This is Physics 1020 and 1090, the lecture for Wednesday, March 25th. We're continuing our review for Exam 3, and here in Video 3, we're going to talk about Practice Exam 3C. The reason I gave you a third practice exam is because it is a timed practice exam. Basically, I wanted to do an experiment to make sure everybody was comfortable using WebAssign under the timed format before we do the actual exam. So, a few things to remember. This is news from the WebAssign. Once you start a timed exam, you can't stop until you're finished. In other words, if you can't start, pause halfway through, go off and do something, come back and restart. So you need to have your 70 minutes there available, a time where you won't be interrupted, where you can dedicate to this class. So you can take this exam anytime on Friday, but you need to make sure that you and all the people you live with understand that there's going to be a 70-minute period where you need to be left alone to work on your exam. Now note, you can take the exam anytime until 11:59 Friday night, but if you start at 11:50, you'll only get 10 minutes, 9 minutes really, to take the exam. That is, 11:59 is the last possible time before the exam turns off. So, do plan to start by, say, 10:30 so that you don't run into a problem where you don't have as much time as you should because the exam turns off at 11:59. Remember, unlike the homework, you get one submission for each question. The questions are going to be in random order. You get one submission. Now, the questions are also going to be all multiple choice, just like they were on the practice exams. And so there's no chance to get partial credit. There's no chance to be on the right track and show your work and get some of the credit because you started right. It's all or nothing. So that means please, please, please be careful with your one submission. It's your only chance for that problem. Make sure you're confident about the answer before you submit. But do make sure you've submitted all your solutions before your 70 minutes is up. So keep a clock or a timer so that you know how much time you have and you don't end up getting the whole exam right but not getting it submitted in time because time ran out. Finally, again, you can take the exam anytime from midnight Thursday to midnight Friday. It's really up to you. So, but do try to plan your time ahead. Few more issues about the exam I want to note. First, it is an open book, open note exam. You can even use the internet if you want, but realize that time is going to be an issue. You don't want to be scanning and Googling for a long time. You want to be able to solve these problems. So I would try to be prepared so you don't have to use the book and the internet. You may want to make a page of notes for yourself, even though it's certainly allowed. You don't necessarily have to with all the other resources you have, but I would advise you to have a page that contains all the key information so that you have it right there at your fingertips. Okay, there's one thing that I can't entirely enforce, but we're going to do it on the honor system. That is, you must do the work yourself. No getting help from other students, either in our class or anyone. No getting help from any person at all. This is your own exam. It'll be on the honor code. That's a requirement. And once you finish the exam, you can't discuss the exam with other students until Saturday. I don't want you discussing it even if you both finish the exam. I would want you to stop and not discuss the exam with anybody until Saturday. If at 12:02 a.m. early Saturday morning you want to text each other about the exam, be my guest. But until the exam deadline is passed, 11:59 Friday night, don't discuss the exam with anybody else. Okay, one reason we have this timed practice exam is because I want you to let me know if you have problems with it, especially with WebAssign or with internet. If you have problems with this timed practice exam, you're probably going to run into the same problems on the exam. The reason we're doing this experiment is to let you get all those problems out. In fact, I think that this practice exam 3C is actually a little easier than the other two practice exams, probably a little easier than what you're going to have on exam 3 itself. The main goal isn't so much to review the material. The main goal is to get any kind of kinks, any kind of problems with taking the timed exam on WebAssign out of the system so that you can go ahead and be comfortable when it comes to exam day. During the exam, if you have a question, you can try to email me. However, I can't sit at my email the entire day Friday and give you immediate responses. So you can give me a try if you have by email if you have questions, but I don't think it's something you can count on. My job is going to be to proofread all these questions extremely carefully, making sure that I avoid any ambiguity. Your job is going to be to try to answer the question best you can, and if you see a problem, email me. You may or may not get an answer in time. Let's start going over the solutions to the practice exam. Okay, the first question was finding the energy of a photon. So we have that the wavelength of the photon is 0.34 nanometers. And the energy is going to be Planck's constant times the frequency, and the frequency is speed of light over the wavelength. So you end up getting the energy is hc over lambda. H, Planck's constant, 6.6 times 10 to the minus 34. You might want to keep some of these constants that you need written out on your sheet of notes so you don't have to thumb through the book or the internet. Speed of light, 3 times 10 to the 8th meters per second. The wavelength, 0.34 nanometers. Nano is 10 to the minus 9. You get 5.82 times 10 to the minus 16 joules. But the question has the answers expressed in electron volts. 1.6 times 10 to the minus 19 joules is 1 electron volt. So you do the conversion, you get 3,640 electron volts, or 3.6 kilo electron volts. Now, kilo electron volts energies, 0.34 nanometer wavelengths. This is down into the X-ray part of the spectrum. These wavelengths are similar to the size of atoms themselves. X-rays, 3.6 kilo electron volts is enough energy to, yes, break bonds. This sort of X-rays, if you were exposed to, could break bonds in your DNA and potentially cause cancer. So these are certainly large enough energies to break many bonds. Problem 2 is a bubble, a thin film problem, which in this case deals with bubbles. Bubble has air on the outside, air on the inside, water in the middle. You have your incident light comes down, and part of it's reflected off the air-water interface, and part of it comes down and reflects off the water-air interface. Now, the thing about these bubbles is that you get a phase change going from low index air to high index water here at this first reflection. But you don't get a phase change going from high index water to low index air on the second phase change. So just on reflections alone, there's a 180-degree phase change between the two reflected rays. Remember, what we're really trying to find is how these two reflected rays interfere to give you, in this case, you're looking for destructive interference. Well, you already are going to get a 180-degree phase change just from the reflections. You also can get phase changes because this ray goes an extra distance, a round trip of 2d, where d in this case is the thickness, 546 nanometers. So you want to have 2d, the thickness, is equal to some integer number of wavelengths, because it's already going to have destructive interference just from the phase changes. So you want to keep destructive interference. You want to have the extra distance give you an integer number of wavelengths. So you're always going to have destructive interference. And remember, when I say wavelengths, I mean the wavelengths in the water. So you have to take the lambda, which was the wavelength out in the air or vacuum, and divide it by the index of refraction of water. And there's going to be multiple solutions. This is going to be true if it's an extra 1 wavelength, extra 2 wavelengths, extra 3 wavelengths, and so on. Even could, in theory, be 0 wavelengths, as this was an extremely thin layer, so the extra distance was negligible. You solve this for the wavelength, you get 2d index of refraction of water divided by m, and that gives you, here, multiple solutions. So let's just make a little table, and we'll see we get multiple solutions for different values of m. You get different wavelengths. And you might say, oh no, I have lots of solutions, but only one of these solutions is in the list of possible solutions on WebAssign, and that is 726 nanometers. So the solution is 726 nanometers, which is, you have a 2 wavelength path difference round trip. So 1 wavelength down, 1 wavelength coming back up. That is thin film experiment. The hardest thing about the thin film problems is remembering these phase change issues. Problem 3 is a critical angle one. I'm going to just use the critical angle equation. You take the ratio of the index of refraction. If you're trying to find the critical angle of some material in air, you get a 1 over the index of refraction of that material. Take the ratio, take the inverse sine, you get 35 degrees. Please make sure you're comfortable with your calculator so you can do trigonometric calculations, both trigonometric ones and inverse trigonometric calculations like you need to here. Make sure you know you're in the degree versus radian mode on your calculator. Problem 4 is going to be a lens problem. Okay, you have a diverging lens. Diverging lens has a negative focal length, -6 centimeters. So, and the object is placed 20 centimeters in front of it, or over here to the left. Now, you don't have to draw the ray diagram, but again, I always encourage it because I feel it helps you make sure you understand the problem and don't make a ridiculous mistake. So let's look at the rays. You have one ray coming in parallel, and it goes out as if it came from the focal length, but for the diverging lens, it's this focal length, and it's as if it bent outward coming from the focal length. You have another ray that's heading to the focal length, but not to the near one, but to this far focal length. It's heading towards that focal length, hits the lens, goes out straight. Another ray goes through the center of the lens, and for both converging and diverging lenses, that passes through with no change in direction. All these are diverging outward from each other over here on the right, but here on the left, they are, okay, sorry, the video seemed to turn off for a second. If extrapolated back, they all come to an image right here. All right, we can say something immediately about that image. It is a virtual image because all the rays don't actually meet here. They just appear to come here. It is upright and it has not been flipped upside down. It's an upright image, but it's smaller than the object, so it's a minified image. Let's do the problem now analytically using the thin lens equation. 1 over focal length equals 1 over object distance plus 1 over image distance. The focal length is -6, negative, it's a diverging lens, equals object distance is 1 over 20, the object is over here on the left, plus the image distance, and you get an image distance of -4.6. 4.6, that sounds right. First of all, the minus means it's over on the left. With lenses, a negative image distance means over on the left, same size as the object. And if the focal length is 6 or -6, but the distance from the lens to this point is 6, then that looks like 4 or 5 centimeters, so it looks about right. Magnification, minus image distance over object distance, minus, and the image distance has a minus, they'll cancel. 4.6 over 20 gives you 0.23, so this image is about 1/4 of the object, which also looks about right. It's a virtual image. The negative image distance is consistent with it being virtual. The positive magnification is consistent with it being upright. And the fact that the magnification in absolute value is less than 1 is consistent with it being minified. You want to be comfortable with these types of lens problems, both for converging and diverging lenses, and similar problems for mirrors, both convex and concave mirrors. Problem 5 is a color problem. You have white light coming in and hitting a piece of paper. White consists of the primary colors red, green, and blue are all present in white light. The light hits the paper and it has some ink on the paper, and that ink is a type of ink that absorbs the blue light. Well, as it absorbs the blue light, your reflected light is just going to be red and green. So red and green light together form yellow. So if you pour ink onto a paper that absorbs blue light, what it will look to you, looking down on the paper, is like yellow, the color yellow ink. So this would be yellow ink. Yellow ink absorbs blue light. You want to be familiar with the simple rules that we discussed about color vision and color addition, color subtraction. Last question is Young's experiment question. Here you have light coming in of wavelength lambda, which we don't know the wavelength. That's what we're going to try to calculate. Let me just remind you, I cannot draw the symbol lambda in WebAssign, so I will probably write it out as wavelength, the English word. It hits two slits, narrow slits separated by 0.3 millimeters. On a screen 17 meters away, it forms an interference pattern. 17 meters is a long distance, much longer than what we did when we did the experiment in class. That's like taking the experiment all the way to the back of our lecture hall and projecting it on the screen from there. 35 millimeters is a large distance between adjacent fringes. Large distance, but that's also because it's being projected so far away. The equation for Young's experiment was the wavelength is equal to the slit separation times the distance between adjacent fringes over the distance to the screen. We use m equals 1 because we're talking about adjacent fringes. So we get, for the slit separation, 0.3 millimeters is 10 to the minus 3 meters, times 35 is times 10 to the minus 3, because it's again in millimeters, divided by 17, and that number is in meters. You can plug this into your calculator, but sometimes I find it useful to just estimate so you make sure you don't make some dumb mistake. 0.3, which is about a third, times 35, that gives you something around 10. Divided by 17 gives you something that's a little more than a half. Call it 0.6. 10 to the minus 3 and 10 to the minus 3 gives you 10 to the minus 6. 10 to the minus 6 is a micron or micrometer. So it should be around 0.6. If you do the calculation, 0.62 microns is the solution. Usually wavelengths are given in nanometers. That's what's given in the answer sheet for problem 6. So you get 620 nanometers as the wavelength of the light. Young's experiment proves the wavelength of light and allows you to actually measure the wavelength of light. Okay, once we get through exam 3, what's next? Remember, we're skipping chapter 26 on special relativity. So we will start chapter 27 on quantum physics on Monday after the exam. That means there's a quiz 27 that's going to do 8 a.m. Monday morning. So you want to get to work on that. We will cover chapters 27 through 30 for exam 4, which is also known as the final exam. And that will take place on April 20th. So we'll go back to having our video lectures and our web assignment homework, our quizzes, and we will finish these last four chapters on introduction to modern physics. So good luck with the exam. Let me know if you have any questions, and then onward to modern physics after we're done.